Hello guys, welcome back to my channel Gamma Di Gamma. Today I will be doing a definite integration essentials video. So let's get to it because it's an important topic and many of you requested me to do a video on the same. So as I said, let's get to it. First off, I would like to explain to you guys that how we approach a definite integration question first. So what is definite integration? This video is assuming that you know what indefinite integration is. So definite integration is nothing else but just integrating a function, but you have lower and upper bounds in this case. And integrating this will give you a primitive function f of x, but you still have the bounds. So how to evaluate this is basically plugging the upper bound in the place of x and then subtract that by the plugged in value of the lower bound. And a primitive function is basically whose derivative equals the original function. So integration is about finding the antiderivative, and when it's definite integration we find the antiderivative and then we plug the upper limit minus the lower limit. Okay, so this is the basic stuff. Now there are some properties of definite integrals. Okay, the first property goes like this. Say you have an integral from a to b of a function f of x dx. This is the same thing as the integral from a to b of f of t dt. So this is saying that it doesn't matter what variable you're integrating with, as long as the argument in a differential have the same variable, and your limits, your upper and lower bounds are the same. As long as these conditions hold true, it doesn't matter what variables you have, because definite integral is basically area under a curve, right? Whether you call the curve x, or you call the whether you call the with respect to what you're integrating x, or you call that t, like the curve is going to remain the curve, because it's a subject of it's a function of that variable, right? Here f of x, here f of t. The second property goes like this. The integral from a to b of f of x dx equals the negative integral from b to a of f of x dx. And now what this says is you can flip the upper and lower bounds, but you have to put an additional negative sign here. The third property says, and I think this is the most important one from an exam point of view, the integral from a to b of f of x dx is equal to the integral from a to b of f of, basically you add the upper limit and the lower limit, a plus b, and then you subtract an x dx. So this is basically what we call exploiting symmetry. So basically this is using symmetry, because a and b, they, if it's helpful we can exploit symmetry, but like in some examples even using this third property doesn't change the original function, so then we have to use other techniques. But most of the times most of the questions are based on third property, so it's very important. Now let's do one example, and I'll just tell you before doing the example that you don't need to use any of the properties I just told you. This is basically like a recap of indefinite integration. So the integral from 0 to pi by 4 of sine of x cosine of x all over sine to the fourth of x plus cos to the fourth of x dx. So now you might notice that sine x into cos x is quite close to the derivative of sine squared x. So let t equals sine squared x, then dt will be 2 times the sine of x cosine of x dx. You can also write this as sine of 2x dx. This is your dt. Now since you made a substitution, now you have to also change the limits of integration. So assuming we call this integral I, so I is now, okay, let's see, when x was 0, you can just plug 0 here. T will also be 0. When x is pi by 4, sine of pi by 4 is 1 by root 2, and then square of that is half. You have to basically plug in plug in for x and then get a corresponding value of t, since you made a substitution. Yeah, so from this you might see that we can actually replace the entire thing by dt over 2. So dt by 2, and then we have t squared plus, then we can write cos to the fourth as cos, the square of the cosine of the square of cos square of x. So well, cos square will just be 1 minus sine square, so 1 minus t the whole thing squared. So that's cos to the fourth power, 1 minus t the whole thing squared, and we already put the dt. So I'll just pull the 2 outside. Integral from 0 to half dt all over, when I open the bracket and simplify shit, 2t squared minus 2t plus 1. You have a half, integral from 0 to half of I would like to plug a 2 from the denominator, so you have another half multiplied now, half into half, dt all over t squared minus t plus half, and 1 by 2 into 1 by 2 is 1 by 4, integral from 0 to half of dt all over. Now we can complete the square. This will be t minus half the whole thing squared, but then if you expand this, it will be t squared minus t plus 1 by 4. So, and there wasn't a 1 by 4, so we need to compensate by subtracting a 1/4, and then this original half was just there. So 1 by 4 integral from 0 to half of dt all over t minus half the whole square. This will be positive 1/4, so I'll just write that as half the whole thing squared. And now there was a special formula for this, and that was 1 over whatever this thing was. So in this case 1 over half is just 2, tan inverse of t minus half all over half, and then since it's a definite integration we have to put the limits like this. This will be half tan inverse. I'll just clean this up, so this will be 2t minus 1, then the 2 gets factorized from half to 0. Now let's plug in the half. So tan inverse of 2 times half is 1, 1 minus 1 is 0, minus half tan inverse of, well, when you put 0 this thing goes to 0 and then you just have the negative 1. Tan inverse of negative 1. Now tan inverse of 0 is 0, so this thing just goes to 1, and we have negative times half times the tan inverse of negative 1. Tan inverse of negative 1 is the negative of the tan inverse, so minus and minus become plus. Half tan inverse of 1. Tan inverse of 1 is pi by 4, then you have this half. Finally we have pi by 8 as the answer. Now let's do another example where we don't again need the properties explicitly. Say you have integral from 0 to pi this time of dx all over 6 minus cosine of x. Well, if you were to argue that why can't we use the property, well, I say go ahead, plug it in, but it will make the question way uglier. And I'm going to do questions where we actually use the property, but since looking at this function, I think we can integrate it without much difficulty. So in this one we will basically use a Weierstrass substitution, or you might know it as the tan x by 2 method. So for that I need to write everything in terms of half angle tangents. So cosine of x is nothing but 1 minus tan squared of x by 2, the angle is half, okay, all over 1 plus tan squared x by 2. If you don't know what I did here, please revise your trigonometry. And simplifying this much more, integral from 0 to pi of well, this denominator is going on top, and 1 plus tan squared x by 2 is the secant squared x by 2. Then the denominator gets cross multiplied with the 6, so we have 6 plus 6 times tan squared x by 2 minus 1, I'm opening this bracket, plus tan squared x by 2. Now I would want to clean this up a bit. Integral from 0 to pi, I forgot the dx, sorry. The secant squared x by 2 all over 6 minus 1 is 5, but let's put the tan squared x by 2 terms first. So 6 plus 1 is 7 tan squared x by 2, and you have a 5, and I won't forget the dx this time. Now this calls for the Weierstrass substitution, because the derivative of the of tan x by 2 is in the numerator, so we can just let u equal tan of x by 2, then du is naturally half sec squared x by 2 dx. The half is because of using the chain rule here, and the numerator is basically 2 du. all over 7u squared plus 5. Now let's plug in the value of x to find the corresponding u. So tan of 0 is 0. Tan of pi by 2 will be nothing but infinity. Hey, look at that. We're getting an improper integral now. But don't worry, it will converge. Now I really want to pull out the 2 and 7. Worthless coefficients, if you ask me. So du all over u squared plus, we'll have a 5 by 7 here, but I want to write it in terms of a square. So square root of 5 by 7, the whole thing squared. And now we can again implement the same tan inverse formula that I spoke of, I applied in the previous example. So this will be 2 by 7 into, then I flip this coefficient, square root of 7 by 5 times the tan inverse of square root of 7 by 5 times u, but don't forget the upper and lower bound, which is infinity and 0. Now in this expression we have a square root of 7 in the bottom. Square root of 7 into square root of 5 is square root of 35 precisely, 2 over the square root of 5 times, now time to plug in the infinity. So tan inverse of infinity, if you know your trigonometry, is pi over 2 minus, time to plug in the 0, tan inverse of 0 is 0, and finally the 2 and 2 cancel out. The final answer is pi over the square root of 35. Yeah, pretty neat answer. Now this third example that I'm going to do is a pretty important one, because it's easy and the board likes to ask such easy questions. So the absolute value of x squared plus 2x minus 3 integrated with respect to x. Now since there's an absolute value, we actually need to profile this function which is inside the absolute value. So we need to know when it's positive, we need to know when it's negative. So one way of doing that is to factorize it. So since it's a quadratic, it should have two factors. Here they are x plus 3 and x minus 1. So from this expression you can guess that the function is negative from, say, well, the function is 0 at minus 3 and it's also 0 at 1. Let me just join this up. So this is going to look something like this, but our integration is from 0 to 2, so we don't care about the negative, the region behind 0. So say 0 is somewhere here. We care about this region and then wherever 2 is. So here assuming there is a 2, so we care about this shaded region, right? So now you must know that from 0 to 1 the function is negative, and from 1 to 2 function is positive. So I can I can rewrite this this integral without the absolute value, and I won't change the meaning. So basically I have to break it up into intervals wherever there was a change in sign. So first the negative bit, the integral from 0 to 1 of the original function x squared plus 2x minus 3 dx, but with a negative sign, because here it's going to be negative, right? And in the absolute value you can't tolerate a negative. And you can break intervals like this in definite integration. So integral from 1 to 2 of x squared plus 2x minus 3 integrated with respect to x, but no negative sign this time because the region is positive. So no changes there. But let's get to integration now. Integrating this is very easy. Integral of x squared is x cubed by 3, don't forget the negative sign, minus x squared plus 3x, but now we have our bounds from 0 to 1, plus x cubed by 3 plus x squared minus 3x. Now our bounds are from 1 to 2. Now you can just plug in 1 once, minus 1 by 3 minus 1 plus 3. Plugging in 0 is, basically making the all the terms 0, so I won't bother writing that down. And then I'm going to plug 2 in the entire expression. So 2 cube is 8, 2 square is 4, 3 2s are 6, minus, then I'm plugging in 1 here. So 1 by 3 plus 1 minus 3. Yeah. And let's just open this bracket up and simplify it. So plus 4 minus 6 minus 1/3 minus 1 plus 3, and simplifying everything, you just get 4. Yeah, you can pause the video and calculate if you disagree. So it's 4. Okay, sorry for keeping you guys waiting, and now we are going to actually use some properties that I showed to you in the initial bit. So I have the integral from pi by 6 to pi by 3 of dx all over 1 plus square root of cotangent of x. Now looking at a function like this, I want to convert everything into sines and cosines. So integral from pi by 6 to pi by 3 of dx over 1 plus what is a cotangent? It's basically the ratio of the cosine to the sine. Now if I can just cross multiply everything properly, I can write this as the square root of sine of x all over square root of sine of x plus square root of cos of x, won't forget the dx. Well, now looking at it, we can actually use properties. So let's again call this I from pi by 6 to pi by 3 by property number 3. Instead of x, I'm going to write as upper limit plus lower limit pi by 3 plus pi by 6 minus x. This I'm going to do this for all the x's that we have here. So sine of pi by 3 plus pi by 6 minus x in a square root plus the cosine pi by 3 plus pi by 6 minus x under the square root multiplied with a dx. And now I'm going to actually clean up the argument part of the integrand. So I have the square root of sine of pi by 3 plus pi by 6. So 30 and 60 degrees is 90 degrees, which is pi by 2 radians minus x all over the sine of pi by 2 minus x plus the cosine of pi by 2 minus x integrated with respect to x. Now, using our trigonometric compound angle properties, sine of pi by 2 minus x is nothing but cosine of x. Same thing in the denominator. We have the cosine of x. Here we have the sine of x dx. Now this is interesting because this, whatever we got, this is I, which is the initial integral itself. This is I, right? This is the initial integral itself. And now this is equal to our question. This is the same thing as this, right? So what I'm going to do is I'm going to add this and this. So I'll have I plus I, or 2i, the integral from pi by 6 to pi by 3 of square root of sine x plus square root of cosine x all over, and the denominator is common, so that's why I could just add the terms in the numerator up directly, dx. And now look at this, everything just blows off to 1. It's the same. So 2i, and then integrating 1 with respect to x is x from pi by 3 to pi by 6 implies that 2i is equal to pi by 3 minus pi by 6, and so 2i is equal to pi by 6 implies that I is equal to pi by 12, and that is the answer. Now I guess to drive the point home, we'll just do one more example. The integral from 2 to 4 of the natural log of x squared all over the natural log of x squared again plus the natural log of 36 minus 12x plus x squared integrated with respect to x. Now what we can do, because this is a horrible integrand, is to use property number 3. Then instead of x we have 6 minus x, the whole thing squared, all over the natural log of 6 minus x, the whole thing squared. And this, everything just simplifies to the natural log of x squared when you plug in x as 6 minus x. So yeah, we can add this I and this I together to get 2i is equal to the integral from 2 to 4 of the natural log of x squared plus the natural log of 6 minus x the whole squared all over, interestingly the same thing in the denominator, plus the natural log of x squared dx. And brilliantly everything just goes to 1. So just integral of 1 with respect to x is x from 4 to 2, and that's just, well, i's will be nothing but 1. And in case you're wondering why I just plugged in 6 minus x is basically upper limit plus lower limit. So upper limit plus uh, lower limit minus whatever your variable was. So in this case 4 plus 2 minus 6 is equal to x. And, yeah, because of property number 3, this won't change your integral one bit. If you want, I could give you a proof of this, but I think this suffices for now. So guys, I hope you liked my video. Please like, share and subscribe. Have a great day and all the best for your future endeavors.